Here we go. We're going to take a look at how energy travels within ecosystems. And you can find this information mostly in chapter 3.6 in your book. And we're going to be covering primary productivity, trophic levels, the 10% rule, and food webs. So here we go. Here are your learning objectives. Take the time to look over them on your own time. I kind of have them scattered throughout the presentation where I thought that they fit, but I did my best. But make sure that you stop and look at these as we go through this PowerPoint. And here is yet another set of learning objectives. A couple of things that I'll just point out is that in these learning objectives, I highlighted biogeochemical cycles. The reason why I did that is because we learned about that in our last lesson, but basically that matter is traveling through organisms by way of biogeochemical cycles. So through uptake and assimilation and, just consumption. So, be aware that that's happening and cycling, and don't forget what we learned before, just because we're moving on to something new-ish. And then also, because this matter is moving through and cycling, it is a conservation of matter. Remember, matter cannot be created nor destroyed. So photosynthesis is number one in what we're talking about today. It takes the sunlight, solar energy, and converts that solar energy into a form of chemical energy. And this is where all of the energy in any ecosystem comes from. Well, I guess in chemosynthesis in deep water systems, but let's stick to photosynthesis for now. But anyway, right, these photoautotrophs are producers that use the sun, right, to capture the sunlight and forming glucose. And so this glucose can then make other compounds, so cellulose and starch, which are carbohydrates or polymers, lipids and proteins, so other types of macromolecules. But it all stems from this, first conversion of energy from sunlight into glucose. Anyway, back to photosynthesis as a whole. It really is a perfect picture of the first law of thermodynamics. So the first law of thermodynamics really says that it's a conservation of energy. So energy cannot be destroyed, but it can be transferred. And so solar energy is transformed. So energy isn't destroyed, it's just transformed into this chemical energy. And then that energy is stored in the bonds of glucose, and then it's released through cellular respiration. So for cellular processes. So what is cellular respiration? Well, just in case you forgot, here is the chemical equation of cellular respiration. And right, it's the process that all organisms undergo to get usable energy for their cellular activities. And really, it breaks down glucose to make that usable energy. And even producers or autotrophs, whatever you want to call them, same thing, yes, they undergo cellular respiration as well. And although they go through photosynthesis, taking in carbon dioxide, they're actually using carbon dioxide also. And so they do end up producing less carbon dioxide than they use. And so therefore they have a net, they're a net sink of carbon dioxide, meaning they hold that carbon dioxide in more than they let go. And so in looking at really how productive an ecosystem is, we take a look at primary productivity. energy that's converted in photosynthesis is what's setting the amount of energy that's available to everything in the system. So all other trophic levels, all consumers are dependent on producers. So really producers are the beginning of any ecosystem. So important. So we look at gross primary productivity, and so that's the total photosynthetic rate, looking over a certain amount of time, whereas the net primary productivity is actually what's super important. I mean, it's all important, right? But what we really want to look at is because this is what takes into account the respiration that producers undergo. So you take your gross primary productivity, subtract it by your rate of respiration, and you end up with net primary productivity. And so net primary productivity is usually measured in a unit of energy per unit of area per unit of time. So if you look down at the bottom of this graph, we have kilocalories, which is a unit of energy, per meter squared per year. And so why do we even bother to look at this is because we can actually look at the amount of energy and how productive an ecosystem is if we compare them. So if you guys look at the graph, you end up with like a tropical rainforest that's like way out near like 8,800 kilocalories per meter squared per year, whereas the desert is much lower. And so we can tell that the tropical rainforest is a lot more productive than the desert because it's undergoing a lot more primary productivity. We can also take a look at the same ecosystem over time, and we can look at how much things have changed. And so in this environmental science course, primary productivity is important because you can actually try and measure the changes that have occurred over time. And so maybe the tropical rainforest was super productive in that certain area of rainforest, but after deforestation, it would decrease dramatically, which would give us an actual quantitative number to look at change. One thing I really want to point out here is on the bottom, you can see that the open ocean and also the continental shelf is actually relatively not that productive. What, you say? How can that be? I thought the coral reefs were the tropical rainforests of the ocean. And yes, they are. But I want you to think about area and how much productivity is happening in the area, how tiny phytoplankton are. And if I were to put a meter square down, how much phytoplankton would I really get? As opposed to going up, into a tropical rainforest and putting down a meter squared, I get a lot more producers in that meter square. So that's why it looks so unproductive. But if I were to maybe look up the total area, it would be highly productive because there's so much ocean and it's so big. But moving on into more about oceans, in aquatic ecosystems, photosynthesis is a little bit, I don't want to say impeded, I don't even know what the word is, but basically visible light decreases with depth. So light does not penetrate water very far, and depending on what wavelength it is. So that red wavelength, that really long wavelength, actually doesn't get absorbed that much. Actually, it stops, I'm sorry, not absorbed, it doesn't penetrate that much. And it actually doesn't penetrate really past 1 meter, whereas that blue light you can see actually goes all the way down to 200 meters. And so depending on where you are in the water column will depend on what spectrum or what colors of light are actually penetrating the water column. And so that means that most photosynthesis is going to occur near the surface because that's where that red spectrum is, which is where chloroplast, that green or the chlorophyll is actually absorbing that red spectrum. And so right? That phytoplankton is going to be way, way up on the surface of the water. Whereas, further down in that sunlight zone where light is actually penetrating, you will get some photosynthesis, but, the organisms there will be a little, they'll be adapted to not having the spectrum as terrestrial organisms do. But beyond 200 meters, basically, there's really no photosynthesis happening. So here is yet another bunch of learning objectives. Take a look at it again on your own. But basically what we're looking at here is the second law of thermodynamics. Oh my gosh, what are you throwing at me, Miss Grant? Well, I'm going to try and make it a little easy for you. Basically, the transfer of energy is not efficient, right? Organisms are not perfect machines. And so that energy that's stored in those chemical bonds get released through cellular respiration, like I said, but that is not an efficient transfer of energy. As it moves up the trophic levels, a lot of that energy is lost as heat. And basically, on average, about only 10% of the energy entering one level passes to the next. So if you have a certain amount of energy as on your producer trophic level, your primary consumers are only going to receive about 10% of that energy, or 10% of that energy will be available to those primary consumers. So a lot of energy is lost. And so while we are looking at trophic interactions, it's really important to take a look at food webs as well. Just coming on back to, freshman biology, a food web is just interlocking food chains. So a food chain is just one singular path, where the food web is all of the food chains that are interacting in an ecosystem. So if we look at one food chain here, we have grass as a producer, grasshopper as our primary consumer, the lizard as our secondary consumer, and our hawk as our tertiary consumer. And so just to bring it on back to that 10% rule, our net primary productivity that's available in the grass, only 10% is available to the grasshopper, whereas the lizard gets 1% of the net primary productivity, and the hawk gets 0.1% of what is available in net primary productivity. So, to kind of bring our food webs up to the next level, right, we're looking at how much energy is available to each trophic level within the food web. Now, because, these interactions are not static, just different organisms can actually be, on different trophic levels. So, for example, the hawk in the example we just talked about was a tertiary consumer, whereas if we look at the star cactus to the kangaroo rat to the hawk, it's really only a secondary consumer. And so the amount of energy that's available to that consumer depends on which trophic level it's actually eating at. And so in looking at food webs, we're going to look at feedback loops. And so just a really brief definition before I get into how it all relates is that a positive feedback loop is a change in the system away from an equilibrium. And a negative feedback loop is where a system is returning to an equilibrium. And so how do these feedback loops actually, relate to the ecosystems as we're talking about? If you look at the top here at this positive feedback loop, you have population is increasing, which leads to more births, which leads to more population, which leads to more births. So we're coming away from our original output, and we are kind of amplifying the effect of the change. And so that's a positive feedback loop where we're coming away from an equilibrium. Whereas on the bottom, if you look at food supply, right? If food supply is going down, then organisms or individuals will die, right? And then if there are more deaths, then there will be more food, and then the population will go up. And then when the population goes up, then the food supply will go down, which means that organisms will die off, and onwards in a cycle where you're coming back to the equilibrium at each point. So let's look at a couple of examples to see if you're clear on this. So there's an abundant prey species, they can support a lot of predators. And if the predators deplete this prey species, then that means the food supply is down, which means that the predators die off. And if there are few predators, and the prey population can increase again, which means it can support many predators, which means that the predators deplete the prey, and onwards and onwards and onwards in a cycle. So what is that? Positive or negative? It's negative. Good job. Okay. And so here we go, right? There are individuals in the populations, and they have offspring, and those offspring have more offspring, who have more offspring, who have more offspring. What is that? Positive or negative? Positive. Good job. All right, and thus concludes Unit 1.